Claire Moore-Cantwell uses cutting-edge tools to address cutting-edge questions, while much work in linguistics focuses on broad generalizations and ignores exceptions to those generalizations. Her work takes on those exceptions. She has worked on probabilistic topics such as phonotactics, stress assignment in English, and comparative adjectives in English. Like, will an adjective take ER or more? She employs a broad range of methodologies, including ERP studies, computational modeling, and constraint-based phonological analysis. She's also interested in gender disparities in question periods at conferences. She maintains a publicly available database for keeping records of trends from conferences with the goal of monitoring the health of the field on this matter. So please welcome Claire.
Thank you. All right, let me get my slides up here. Okay. Great, thank you for that introduction. So today I'm going to be focusing on basically a computational problem. I will be discussing a little bit about the comparatives actually, so I'm happy that you mentioned that. Okay, so I'll be presenting a model and a little bit of, results from that model, I guess. Okay, so this sort of starting really high level here. We're talking about basically the trade-off in language learning, or just language usage, I guess, between memorization of like specific details and abstraction of big patterns in the language. So an example here is about this word stable, which you have to learn if you're an English speaker. You have to learn lots of really specific things about it, including what it means, but also things like how you can use it in certain contexts and not others. But there's certain things about it you don't have to memorize, like that the T is unaspirated. Okay, so that's like a phonological feature that you don't have to learn. You don't have to learn it because there's these broad generalizations in the language that tell you where you should put aspiration. So things that are true of all the words don't have to be memorized for specific words. So the sort of big picture question here that a lot of my research addresses, and certainly what you're about to see today, is how do humans integrate abstract patterns about their whole language with idiosyncratic properties of individual words? Okay. So today we're going to be focusing not on words really like stable or abstractions like where does aspiration go, but rather on things that vary. So there's two kinds of variation that are relevant for today. So one of them is just variable phonology. So an example that I'll go through in detail of this is the comparative in English. It's sort of about like choice between two different versions of the morpheme, but they're highly conditioned by phonology. So I'll be thinking about it as a phonological pattern today. So there's variation here. You can say yellower, you can also say more yellow, you can say happier, you can also say more happy, you can say clearer, you can also say more clear. But the probabilities of these things can get pushed around by a lot of different phonological factors, like whether the word ends in an R or an L. We don't like to put two liquids next to each other in English if we can help it. So we try to avoid saying things like clearer and choose more clear instead. There's other factors that are maybe less obvious, like monosyllables tend to prefer the shorter suffix rather than the, I guess, longer, still just a single syllable, but longer version of the comparative. Then on the other hand, the other kind of variation I'm going to talk about today is variation that you see within individual words of the language. So basically what this is that not all, you may have even a variable grammar, but not all words of the language obey the grammar equally. So an example here, also from the comparative system in English, I want you to just think about the words on the left, real, ready, apt, and false, versus the words on the right. So the words on the left really don't like to take So realer, readier, apter, and falser are not as good as more real, more ready, more apt, and more false, at least in a corpus. On the other hand, the words on the right prefer to take so paler is better than more pale, steadier is better than more steady, and so on. And I've chosen these examples carefully to sort of illustrate that it's not really about the phonology. So real and pale are pretty similar phonologically, so are steady and ready, apt and sharp, etc. Okay, so there's sort of these two kinds of like variation and idiosyncrasy that we're looking at, how they interact together. Okay, so the variable phonological patterns we can model using a probabilistic grammar. So probabilistic grammar would just be any kind of phonological grammar that predicts a probability distribution over options instead of just giving you this is the correct way to say the word. It says like, you know, say it this way 70% of the time or something like that. The words that deviate from the grammar will need to be some kind of lexical listing. But how exactly to model that lexical listing is not actually super straightforward, as it turns out. So I'll discuss a couple different ways to do it. And in the end, I'll be arguing for a theory of mine, representational strength theory, which I'll get into. Okay. Okay, so to sort of summarize, the goal is to model both variable phonology and lexical exceptions. I'm going to focus today on the effect of lexical frequency on words' degree of exceptionality, something that I'm calling C-shaped idiosyncrasy after what the graphs look like. I'll show you a bunch of those. And then I will present representational strength theory, which is a theory of mine. The basic idea in this theory is that features of words are learned along with the phonological grammar. So you're learning the grammar and you're learning the lexicon at the same time. Different features of a word can be gradiently represented, which means words can be gradiently exceptional. So they can be strong exceptions or weak exceptions or not exceptions at all. And this theory predicts the emergence of this particular pattern of C-shaped idiosyncrasy. Okay, so just to get into that frequency and idiosyncrasy thing, this is a pretty sort of, I don't know, clear case of a sort of well-known fact about language, which is that generally higher frequency things are more likely to be exceptions, are more idiosyncratic in general. So I've got just a graph here of regulars and irregulars in the English past tense system, kind of a classic case of it. You can see that the frequency, which is on the x-axis here, can people see my mouse? Yes? Okay, so the frequency is on the x-axis here. You'll be seeing lots of graphs like this in this talk today where the frequency is on the x-axis. So, and then the number of words that sort of exhibit a particular past tense is on the y-axis here. You'll notice that the exceptions have their own y-axis because there's so few of them. But the exceptional past tenses in English are sort of clustered at the high end of the frequency distribution, and the regulars are, I guess, clustered lower. There are high frequency regulars too, they're just obscured. But the idea here is that greater experience with particular forms as you're sort of learning language leads to more complex representation and resistance to things like language change and resistance to the effects of the grammar in general. Okay, so let's talk about this C-shaped idiosyncrasy that I mentioned before. Okay, so just so you sort of immediately see it, here's the C. Okay, so this is a graph of the English comparatives. So as I said before, they vary between taking more as the comparative, taking more as the comparative and taking as the comparative. And here the y-axis is the probability that a particular word will take and then each dot is adjective of English. So this one is the word nimble, which takes about 28% of the time. Noble takes like 60% of the time. Stable almost never takes and simple almost always takes Okay, so there's two things going on here. One is that the grammar is variable, which we can see kind of in the lower end of the frequency range. We see a lot of variation. And in fact, this variation is conditioned by those factors I mentioned before. So just phonological factors about the word, its length, the phonemic content, and so on. So higher frequency words will diverge more from the grammar. So you can see that they kind of behave differently than the lower frequency words. But there's a second thing going on here, which is that the higher frequency words also exhibit stronger preferences. So we see kind of like this, I mean, in this graph, mostly the extreme forms are up here, you know, almost always taking but you see a few extreme cases that almost always take more around the bottom of this graph. And so that's kind of the stronger preferences piece of it. Okay, so this comparatives case is not the first case that's been noticed of this sort of C-shaped distribution. Morgan and Levy have a paper from 2016 that looks at binomial expressions in English, which are things like ladies and gentlemen, name and address, bread and butter, and so on. Just like the comparative, there's sort of an array of grammatical factors that condition the choice between them. So there are things like the length of the word. Some of the factors are syntactic or semantic. Some of the factors are phonological, like stress clash avoidance. But the point is there's a bunch of grammatical factors. And low frequency pairs, or totally new pairs, like these gray ones here, vary according to those grammatical preferences. But high frequency pairs, like ladies and gentlemen, exhibit idiosyncrasy. So it's really quite weird to say gentlemen and ladies. Mostly, we sort of know that that form has to go in that order. And the same thing is true for these other examples that I've given here. Okay, so in their experiment, so Morgan and Levy did basically a judgment experiment, and also some processing experiments as well. So the stuff is also relevant for processing, but I'm not really going to get into that today. So on the right here, you can see a graph from their paper where what's going on here is actually, so the x-axis here is the proportion that's in alphabetical order. So because it's just like, which order are they showing up in? We can't say like the Moore version or the version like we can with the comparatives. So it's just a way to kind of categorize words. But what you can basically see is the ones that are attested in the corpus have sort of preferences to either be one way or the other. There's not very much in the middle. This graph is novel pairs, like bitter and purple, bishops and seamstresses, things like that, and those kind of cluster in the middle. So people don't have as strong preferences about them. Instead, they're sort of choosing probabilistically based on the grammar. Okay, so this is another case of that same sort of C-shaped idiosyncrasy that we saw for the English comparatives. And they basically characterize this as a trade-off between abstract knowledge, which I would call grammar, or I will call grammar in the talk today, while reliance upon direct experience increases with increased exposure to an expression. So they bring in this idea that like, well, of course, the more frequent forms have more idiosyncrasy because you have more experience with them, so you can learn idiosyncratic things about them, basically. So experience leads to changes in specific lexical items. Okay, here's a few more cases of this C-shaped idiosyncrasy that I've found in the literature. None of these folks, by the way, point this out as like a thing that they found, but you can sort of see it in the graphs in the paper. So this one's probably the weakest case, but it is an interesting one because it's kind of syntactic in nature. So this is basically, we've got frequency, again, on this x-axis, and then each dot is a verb of Spanish. And then the y-axis is basically how often is the pronoun actually expressed. So Spanish, you don't have to express the pronoun. I mean, it's also this is also conditioned by lots of other factors. But just looking at the identity of the verb, we do see a relationship with frequency where the higher frequency verbs tend to kind of diverge. Over here, we've got Korean vowel harmony. So basically, does a word exhibit vowel harmony or not? Many words vary, but as they get more frequent, we see this kind of more extreme behavior. One thing I do want to point out before we move on is that in many of these graphs, you'll also see like extreme behavior in the low frequency items. And that's just because they're low frequency. So we don't really know the true distribution of these words because this is like from a corpus, for example, we may have only one example of that word. So it would either be 100 or it would be 0. So that part's not very important. I guess try to just sort of ignore that end of the graph. Okay, so here's two more. These graphs are a little bit wobblier because they weren't from actual papers. I got this one from the author directly. I got this one from some supplemental materials. But here are basically two more cases. So this one's also from Korean, and it basically has to do with tensing of stops in compounds. So how frequent is the compound? Basically, the more frequent compounds have more extreme behavior in terms of how likely they are to undergo tensification. Over here, we've got Hungarian genitive choice. So there's two options for the genitive in Hungarian, and how frequent the word is determines how extreme its behavior is in terms of like which option for the genitive it prefers. So some words that are kind of middling frequency vary quite a lot. Like this word varies quite a lot, but the higher frequency words have more extreme preferences. So these are some more cases of this C-shaped idiosyncrasy. All right, so to summarize so far, in general, we already sort of know this, higher frequency forms are more likely to be exceptions. C-shaped idiosyncrasy is a special case of this, with kind of two things going on. So one is that same, high frequency forms diverge from the grammar. Two is that the high frequency forms don't just diverge randomly, they also exhibit more extreme behavior than low frequency forms. So the high frequency forms will tend to be sort of categorical in their own behavior, even though the general pattern in the lexicon might be variable. Okay, so I just want to point out so far that Morgan and Levy's trade-off between sort of abstract knowledge and experience with particular forms explains the first, but not the second. So the increasing experience basically means we should be able to learn any kind of pattern of behavior very precisely for high frequency forms. So we don't yet know why, why they also exhibit that sort of extreme behavior. And so what I'm going to argue today is that this arises over generations from basically overshoot. So like if you are a high frequency form, you'll sort of get like pushed to one extreme or the other because over time, the frequency of that particular form will experience kind of a rich get richer situation. So its frequency will just sort of keep rising until it winds up in one of these extreme positions, whereas low frequency forms don't do that. Okay, so the proposal today will be to model the joint acquisition of exceptions in probabilistic grammar with a goal towards explaining this C-shaped idiosyncrasy. I'll use an iterated learning simulation, which I kind of hinted at a second ago by talking about change over generations. So it'll simulate the transmission across generations. So first I'm going to kind of present like a model of this acquisition process, and then at the end I will present an iterated learning simulation where we sort of begin with like a base state, which is a made up data set basically that exhibits no difference in behavior across frequencies. So all words of any frequency behave the same as each other. And then I'll basically apply the learning algorithm to that base state, use that result as input to the next generation, and so on. So across generations, we'll see that this C-shaped distribution can emerge if the grammatical conditions are good. Okay. So how to model probabilistic grammar. I'm going to use maximum entropy grammar, which is based on optimality theory. So it's a constraint-based grammar. Here's a little optimality theory tableau. I'm just going to be using these two example constraints. This one basically says if you're a monosyllable, you should take It's not really a normal Martinez constraint, but it's what I'm going to use to illustrate things today. It's in conflict with the OCP, which is basically a constraint that says don't have two things next to each other. In this context, what's going to violate this constraint is an L or an R followed by the suffix "er." So pure violates it, but more pure does not. However, more pure violates this constraint, which says the monosyllables should take "er." Okay, so that's just an optimality theory tableau. This constraint outranks this one, so this candidate wins. Maximum entropy grammar adds a couple things. So the first thing is just a set of weights. So in this case, I've given this constraint a weight of 2.5 and this constraint a weight of 2. We can use those weights together with the violations to calculate a number for each candidate. So the measure of like how good it is according to the constraint set, which I've written as H here, which stands for harmony. You can see the official equation for it down here. All this means is just take the weights of all the constraints, multiply them by the violations, and sum. That's all it means. And then we can transform this basically into a probability distribution. So the candidates that exhibit a better harmony, which is closer to 0. So the higher harmony or the closer to 0 harmony is better. The candidates which exhibit a better harmony will get a higher probability. The ones with the worst harmony will get a worse probability. Okay, so that's the model I'm going to use for probabilistic grammar. It's a pretty, I don't know, commonly used model, at least these days, for probabilistic grammar. Okay, oh, one last note, this predicts intra-speaker variation. So a given speaker, if this is their grammar, a particular speaker should produce pure 62% of the time and more pure 38% of the time. So it's not a model of our population, it's a model of an individual. Okay, so what do we do with a word whose behavior deviates from the grammar's predictions? This actually gets a little interesting when we're talking about probabilistic grammar, because anything that exhibits either a different probability distribution or a no probability distribution at all, a word that just only has one thing it does, needs an explanation. Okay, so let's take an example. So real, I've changed out pure for real here. So real is a word that really doesn't take at all. So I don't know what everyone's intuitions in the room are for this, but realer sounds pretty bad to me. More real is a lot more common in a corpus. So we really don't want to predict 62%, 38% for real, because that's just not what we observe. That's not what people's intuitions are like. The other kind of word we need to consider is a word like pure, which I didn't tell you before, but pure also doesn't match exactly the sort of 62-38% distribution, which is sort of the overall distribution we might see between two words that look like this, but pure particularly deviates, but it doesn't have an extreme distribution. It's just kind of a little different, right? So the version is like a little more likely than the grammar predicts. And by the way, these probabilities are coming from a corpus, the corpus of contemporary American English. These calculations are from a paper that I did with Brian Smith a few years ago. So if you're curious like more about this particular case, that's the paper. Okay, so how do we get individual words to behave the way they should, even though the grammar is probabilistic? One obvious strategy we can employ is faithfulness, right? Faithfulness is what we're supposed to use in constraint-based grammars to get individual words to sound like themselves. Okay, so I've added a faithfulness constraint in here, but I've also had to do something else. I've had to just make it be the case basically that the underlying form or the input to this tableau is the full form more real. So I'm not combining more and real anymore, or like real and the comparative. In order to be faithful to an underlying form, there has to be one. So I can't just compose this. I can't choose between and more on the fly. I have to say like that's now in the lexicon, that full form, and so I can be faithful to it. And so that's pretty nice. That gets us more real. That's great. This aspect of it where you have to create a lexical entry might seem a little bit strange, but it's not really all that weird. So I have a couple papers here. The second one is a really cool psycholinguistic study that basically demonstrates they're able to sort of see people sometimes accessing a listed form and sometimes accessing a composed form, and it affects their rate of aspiration. So that's pretty cool. So we know that people do store at least high frequency forms sort of whole like this. They don't always compose them. Okay, so then what do we do here about a word like pure? So pure is not one thing or the other, it just has a different probability distribution than the grammar predicted. In particular, it doesn't have that, like, I think it was 62-38, it has like 85-15. So the way the sort of faithfulness approach would explain this form is to say, well, sometimes it's accessed whole and sometimes it's composed. When it's accessed whole, it's 100% faithful. When it's composed, it follows the grammar's distribution. And so somewhere between this like 100% and 62%, we get that 85% that we want. Okay, so that would be sort of the faithfulness approach. And I'm not totally, I guess there's sort of maybe more work to be done to see if like these probabilities really work out, but at least conceivably they could. Okay, so here's another approach, which is constraint indexation. So the idea here is that we basically make a copy of each constraint, and we say like, this is this word's version of that constraint. So here I've taken this one and given pure its own version of it, and that has a little bit of weight, which can then predict the perfect probability distribution for pure. So this kind of approach can fit really any lexically specific probability distribution easily. It's a really easy time with it, whether the word just has a little bit of a different distribution than the grammar's predictions, or whether it has very extremely different, as like an extreme probability distribution. Okay, so I didn't really talk about problems with the faithfulness approach because I'll talk about those later, but I'll talk about some problems with constraint indexation right now, which is, first of all, it's not so obvious what to do with novel words under this circumstance. Like, do they get no indexation, which means they should maybe behave in ways we don't always expect? Do they get they get some kind of like arbitrary indexation? Is not completely clear. This paper, Becker et al., does a little bit of work to try to address that, but it's sort of not obvious. Worse problems, though, I include things like what morpheme actually gets the index. So is it weird to have a constraint like this one, which tells you what the comparative ought to look like, but it's indexed to this root? So that's another sort of problem with constraint indexation. And then the one that's kind of a deal breaker for today is basically how many possible index constraints. It can really get out of control very easily. And because of that, I actually won't be presenting modeling work with this one today because I wasn't able to figure out how to kind of keep the number small enough that it was computationally tractable to do the iterated learning across generations. Okay. So the third option that I want to present is my own theory, which is representational strength theory. This is a model that's kind of derived from the constraint indexation approach. So elements, but instead of having index constraints, basically we're having like gradient weights, but they're a property of the lexical entry itself. So here's some properties of the theory. Elements of a lexical entry are gradient. So a word might have gradient voicing on one of its sounds or something. Which means that memory resources can be allocated efficiently. Predictable features and elements wind up becoming stronger, weaker, whereas unpredictable features and elements wind up becoming stronger. So if part of a word is sort of less predictable according to the grammar, it will have to be represented more strongly in the lexicon. The way this actually works practically is that lexical entries consist of not underlying forms like a string of phones, but instead they consist of phonological form constraints, which assign violations just like a regular constraint, but they're affiliated with a particular lexical item and they make a particular demand about the surface form of that lexical item. So they make a demand like, well, I'll show you some examples in a sec, but like, the first sound ought to be voiced, the second sound ought to be labial, that kind of thing. And those demands can basically compete with the Martinus constraints in the language. So now the grammar is only Martinus constraints. I'll also present a little learning algorithm for these PFCs. They're learned gradually and unnecessary ones decay over time. So those are kind of the main points, is that they're induced only when you need them and they decay when they're not used. And that's why you get this like predictability, strength of representation trade-off. All right. So here's just a quick example. So I have this real case again, and it's behaving exactly like the faithfulness constraint, except for that this is a constraint that only applies to the word real. And basically this constraint says the word real should take more in the comparative. So we're assigning a violation to any output which does not take the more variant, which in this case is this one. The word will also have a bunch of other phonological form constraints, things like, that make specific demands about the content of the segments in the word. Okay, so here's a whole sort of like blown up a little bit tableau with some examples of these. So I've just got candidates that kind of don't have the right form in various ways. The vowel is wrong in height, the vowel is wrong in backness. Here, the L has been swapped for R, which violates a phonological form constraint that demands it to be lateral. And then finally, I want to just emphasize that because this has two morphemes in it, the second morpheme is going to contribute its own phonological form constraints as well. So this one, actually, I didn't write it in here, but this should have a violation as well. So this one says that comparative should have a nasal in it, which it doesn't if it shows up in the version. Okay. So just to emphasize, there's no faithfulness constraints in the system at all. The underlying form isn't a string that you can be faithful to. Instead, it's sort of this list of constraints that competes with Martinus constraints. Okay, so PFCs are the phonological part of the lexical entry. And so if you want to think about this psycholinguistically, you can think about their weight as like memory resource allocation. So a phonological form constraint with higher weight indicates like, I have decided that this part of the word is worth remembering, and I'm going to allocate a lot of resources to that. Okay, so how do you actually learn these? So I use error-driven learning. So this is just a scheme of error-driven learning in general, not representational strength theory in particular. But basically, the way this works is you start out not knowing what the grammar is at all, but you have some data. You guess values for the constraint weights, which usually the first guess will be they're all 0, but it could be anything. Use that guess to predict an output for a word. So it will learn a single word at a time. So maybe it'll learn, it'll get the input pure, I guess, and it will say, okay, I need to see what I predict for pure, and then check that prediction against the observed output. If it makes an error, it will basically adjust its guess for the constraint weights. If it doesn't make an error, it does nothing. So that's why it's called error-driven learning, is because it only learns when it makes a mistake. So here's an example. Usually the starting guess is that all weights are at 0, and then you just kind of like keep changing the weights gradually over time. And furthermore, in the simulations I'll be presenting here, it's actually really crucial that words are sampled based on frequency. So you'll learn more often on more frequent words. That's not always the case with these learning simulations, but for this research today, it's really important. Okay, so here's an example. Suppose we have the grammar that I presented before with these two constraints, and their weights are 2.5 and 2. And we sample the word paler. So that's the output. And we know that it comes from the lexical entry pale and lexical entry comparative. And we predict this distribution. So how do we get like one predicted form from this distribution? Okay, well, we'll sample one of them. But suppose, most of the time or more often we're gonna sample paler, which would be correct, and then learning would not happen. But suppose we sampled more pale, which would still happen almost 40% of the time. So that's incorrect. It does not match the given input here. So what we'll do then is basically update the grammar, which in this case is the weights on the constraints. And the strategy here is basically to decrease the weight of any constraint that favors the incorrect outcome and increase the weight of any constraint that favors the correct outcome. And we'll only change the weights by a tiny bit at a time. So for simulations I'm presenting today, I've chosen 0.01 as the amount that the weights change. It's just a little bit at a time. It takes a long time, many inputs for the system to actually learn the complete grammar of a language. Okay, so here's just the weights will change a tiny bit, which means the probabilities will change a tiny bit. So nothing will be that different after one update, but after several updates, the thing will start to make different predictions. Okay, so how do we get those phonological form constraints in there? Okay, basically the way this will work is that on a given learning iteration, you have kind of one extra option, which is to also induce a phonological form constraint. So if you make an error, so if we, again, just as the same picture as before, if we randomly sample more pale, which does not match our observed pronunciation, we'll update the weights, but then we'll also induce a new constraint for that specific form that we're working with. And this can have a pretty high weight. So I've given them a starting weight of 10, which is quite high. So it'll basically get that particular form correct instantly. Whereas the general weights of the grammatical constraints will still change quite slowly. Okay, so I just said induce a phonological form constraint, like that's an easy thing to do. Here's how it works. At the start of learning, so you won't induce one every single time. At the start of learning, you will sort of always do it. But as you go on, you'll consult your existing lexicon to decide. So for example, if you have a feature in your language that is not contrastive, that you never need to remember, over time, you won't really consider inducing it. So the idea here is basically to distinguish between errors and actual exceptions, so between things you actually need to remember and things you don't. And so the way that lexical consultation happens is basically check your lexicon, grab a bag of words. I'm using 20 for the size of that bag of words, but it's a parameter that can be set. If any of them have the feature you're looking for, and code a new PFC for that feature. Okay, so the idea, what you need to remember here is basically you don't always induce a phonological form constraint, but if it's a feature, if the feature in question is something that tends to be contrastive, you're more likely to. Okay, Finally, the important part is that these phonological form constraints will decay over time, sort of like how memory decays over time. I've set them all to all decay at the same rate, which is quite small, 10 to the -4th, so they'll decay pretty slowly. If they are decayed all the way to 0, they're removed from consideration, although if that starts to create errors, they could be added back later. But keep in mind, even when they have a very small weight, they won't have that much influence. So if having a small weight means there's errors, their weight will probably get boosted anyway. All right, so let's look at some results from this model. So this is the model of joint learning of exceptionality and probabilistic phonology. And I basically want to start by showing you a simulation learning an existing C-shaped pattern. So this is a simulation for the English comparatives again, which is from that same paper, joint work with Brian Smith from 2017. So this is just a simulation of existing English comparatives. We looked in this corpus COCA, so with about 5,000 adjectives. And there's several constraints in the system that I'm not going to get into, but they basically one for each sort of phonological conditioning factor. And here are the parameter settings, in case you want to know, but I think I went through all of them already. So the phonological form constraints have a pretty high starting weight, but the actual Martinez constraints change relatively slowly. All right, so here is the observed probabilities for a bunch of adjectives in the corpus. So I showed you kind of this much of the picture at the beginning of the talk, so you can now see the low frequency forms. They look weird because they're low frequency and there's not that many instances of them. So there's, like down at the bottom here, there's only one example in the corpus, so it's either 100% or 0%. That's why they look extreme down there. Not because that's the true probability for that word. Okay, so here is the learning algorithms predictions, which, as you can see, match really well at the sort of high end of the frequency spectrum and don't match super well at the low end of the frequency spectrum. And in fact, it predicts categories of things, sort of distinct groups, which are based on the grammar. So like this group here is like one syllable words and end in a cluster, for example. This group here is words that are 2 syllables long and end in R, and so on. So basically the prediction for low frequency items is that their behavior should be entirely determined by the grammar, whereas for high frequency items, they're more idiosyncratic. Okay, so why is this happening? Because the high frequency forms have phonological form constraints about which comparative they should take, and the low frequency forms don't. The low frequency forms don't have them because, first of all, they are not looked at very much in learning, so there's not enough time to actually induce one of these phonological form constraints and keep it in memory. Also, because they're not looked at very often, if a phonological form constraint is induced, it often just decays away and doesn't come back. So they don't provide quite enough benefit to actually stick around for these low frequency forms, which tend to be variable anyway. Okay, so that's, sort of one case of like real data. So let's look at that iterated learning simulation that I mentioned earlier. Okay, so this basically, the way this is going to work, I'll start off with sort of a toy set of data that's like a starting state. So I gave it 1,000 words, and no matter what frequency they all take the exact same rate of Moore and I've also drastically simplified down the grammar, so it's just there's just one Martinez constraint, which basically has a weight that says like take and so all the words behave, in the starting data set, they all take Moore half the time and half the time. So it's sort of a perfectly variable pattern. All words are variable. Nothing really differs from anything else in terms of frequency or for any other reason. However, there are more frequent words and less frequent words. So I put them in the Zipf distribution, just like natural languages. There's fewer high frequency words, many low frequency words. And then each sort of simulated generation learns, and then its final state becomes the input to the next generation. So we start off with this like starting state, put it through that model that I just described, and then its final state will become the data for the next generation and so on. Okay, so let's look at an example. Okay, so here's some input data. Just like I said, no matter what frequency, this is log frequency on the x-axis again, no matter what frequency, everything takes half and half. Okay, so this is after one generation. We can already see that the low frequency words are behaving different than the high frequency words. And by generation, even already here, but definitely by like generation 5, we're seeing that really clear C-shaped distribution. So over time, actually the grammar is also kind of moving around a little bit. That's kind of an interesting point in this, but it's never getting categorical. It's never turning into like, well, just always take more, always take It's staying probabilistic. And then the high frequency forms are basically becoming more and more idiosyncratic across the generations. Okay, and then here's the actual English comparatives, or at least the high end of the frequency scale for comparison. Okay, so just to convince you that I didn't cherry pick this trial, I ran it 8 times. And here is the 10th generation. So, sorry, let me go back here. So this is generation 5, this is generation 20. I figured by 5, they tend to kind of already have the C. So 10 is like in between these two. All right, so this is generation 10 for 8 independent runs. As you can see, most of the time we wind up with something sort of C-shaped. Well, I guess I say most, but it's roughly half. And then the rest of the time we're sort of by generation 10 on our way there. So there's a lot more variation in the high probability or high frequency forms than in the low frequency forms. And so we sort of have this like relatively stable grammar, which can move a little bit but remains variable. What else about this? Oh, I would just like to point out that these forms here, so there's this thing that happens with this learner where like if it happens to induce a phonological form constraint right before I stopped learning, it will just have a high phonological form constraint weight. So there are sort of extreme examples throughout the probability distribution, but the bulk are not extreme unless we're in sort of high frequency land, especially in like these 2 simulations and this one, and also this one. Okay. Okay, so I also tried this with faithfulness. So one sort of like alternative explanation is, well, you don't need all these phonological form constraints or anything. You don't need this gradients. You can just say, well, high frequency forms exhibit more extreme behavior because they're added to the lexicon as whole forms, and low frequency forms are not. You have to compose them all the time. And then forms in the middle, maybe they are listed, but you don't always access them because they're low frequency, right? So the idea here is basically to try a model where we're using faithfulness instead of those phonological form constraints. And words, the higher frequency a word is, the more likely it is to be actually stored in the lexicon, and also the more likely it is to be accessed when the model is actually trying to produce that form. Okay, so in this system, I gave words a 10% chance of getting encoded in the lexicon, no matter what frequency they were. But higher frequency forms, because they're seen more, they are more likely to eventually get encoded in the lexicon. And then on each run, there's, it's probabilistic whether you access the stored form or whether you don't access the stored form. Okay, so let's see what that looks like over time. So again, these are the 10th generation of several runs. Okay, so what's going on here? Basically, there's really consistent behavior for this model, and it doesn't look like the C-shaped probability distributions. So the first thing that happens, even by the first generation, which I'll show you those pictures on the next slide, even by the first generation, under this faithfulness approach, what actually gets learned is not probabilistic grammar. What gets learned is a rule and then a bunch of exceptions. And so that's what we see. So we still see like high frequency forms diverging from the grammar, but we don't see a probabilistic grammar anymore. The low frequency forms do not vary. And so they just follow the grammar, which is categorical. So that's a substantively different result than what we were seeing a second ago for the phonological form constraints. Okay, so high frequency exceptions are learned and preserved over time with faithfulness, but the probabilistic phonology is not. So this is a couple of pictures that are just after a single generation of learning. A couple examples that were sort of clear. So you do kind of have some more variation in these than what you saw after that 10th generation, but already after one generation, the grammar is completely categorical in each case. So this doesn't explain the sort of high frequency extreme behavior. Or I guess it sort of does, but it doesn't explain the other part of it, which is that the low frequency forms vary. Okay. So let me wrap up. So to conclude, I presented this concept of C-shaped idiosyncrasy, which is just a pattern that various languages exhibit, or various patterns in various languages exhibit, which is that variable grammar applies to low frequency forms, but then the high frequency forms not only deviate from the grammar and exhibit their own sort of idiosyncratic distributions, but they also exhibit more extreme behavior tending to not actually vary, even though the grammar may predict variation. I've also demonstrated that C-shaped idiosyncrasy emerges across generations if lexical entries can be represented gradiently. I didn't show you sort of a contrasting simulation for this, but learning has to also proceed according to lexical frequency, such that learners get more experience with high frequency forms. If you don't sample according to frequency in the learning process, you won't get this distribution, obviously, because you're not getting more experience with the high frequency forms. Okay, so I presented representational strength theory today, which is a model and a learning mechanism for probabilistic grammar and lexical idiosyncrasy. It predicts the emergence of the C-shaped patterns, but I just wanted to mention some other problems that the model is good at too. This is not the only, this is actually what it was developed for. It's really good at things like gradient contrast, where something may be not completely contrastive in a language, but contrastive in certain contexts, or maybe there's just a few exceptional forms or something. It's good at other kinds of effects of frequency on exceptionality, such as, really high frequency forms don't have to necessarily affect the ultimate grammar learning, because they can just get, they can get represented as exceptions and they no longer affect learning. It's good at learning either underspecified or overspecified lexical representations, because it just doesn't have to have a PFC, a phonological form constraint, for things that don't have to be don't have to be part of the lexical entry. And it can also have competing phonological form constraints, which lead it to be pretty good at learning allomorphy, which, like the English comparative actually with Moore versus but problems like where there's sort of just a little bit of difference between the allomorphs, but hard to phonologically explain, like on in English, where there's just one segment different, but that segment difference doesn't represent a general alternation in the language. It's just about that one word. Representational strength theory is pretty good at those as well. Okay, thank you for listening. Thank
you so much. And now please ask questions.
Go ahead, Aaron. I don't know if I'm taking questions or if someone else is. But
hi. So you mentioned direct OT, and I'm curious about that. How specifically RST and direct OT differ?
Okay. So direct OT, I think there's like a similarity in spirit, but the details wind up being quite different. So direct OT, the reason it's called direct OT is because the idea was, well, maybe we don't really need to have faithfulness. Like maybe we can just have the grammar like completely, maybe we can have the lexical entry like sort of speak for itself, I guess, in the grammar. So that part's similar, but direct OT, the way it does it is not by something like phonological form constraints. Instead, the lexical entries are encoded in terms of which Markness constraints they violate. And actually, he winds up having to also put faithfulness constraints back into the system in the end as well, because violating some faithfulness constraints is okay, violating some Markness constraints is better than violating others, and the faithfulness kind of captures that. I don't know if that makes sense.
Yeah, thank you.
Mm-hmm. Go ahead, Aniello.
I have this was great, by the way. But so I have a minor questions, but I was wondering whether you can clarify the role of memory in your system. So you were talking about how you allocate more memory to some words than the other, and it's kind of an efficient kind of memory allocation. But then I don't know whether I was misunderstanding that. Does that imply that for you, that interacts with how the more frequent words are going to decay less than the others, or there is nothing to do with it?
Yeah, so the decay is that efficiency. So the idea is basically the idea of memory really only gets into the model through the decay term. So the decay term is basically meant to say, like, you slowly forget things, but if you use them, if the model uses a phonological form constraint, it will like boost its weight if it needs to, right? So that's kind of how you get stronger memory for the more frequent things, is because you just touch them more in learning.
Yeah, thanks. Makes sense. I just wanted to make sure that.
Yeah. Go ahead, Aaron.
Okay, so yeah, so I'll ask another question. I'm curious about why the two models you showed us get different results. In particular, what is it that stops the RST model from ever ending up in a categorical trap? Why does it always? Why do you always get variation? Why don't you ever get on one of these runs? Why doesn't it ever happen to fall into a categorical situation?
So two things. First of all, I don't know that it never does. I haven't run it, like, it's kind of computationally intensive to run one of these iterated ones, so I haven't done it that many times. And also maybe like after a while it could eventually get there. But I think the main thing is just that there's nothing making it's very easy for this model to learn like a probabilistic grammar. And the phonological form constraints don't really hurt that in the same way that the faithfulness does.
Okay. So as you were presenting it, I was wondering why you don't get a majority effects. You might expect that one pattern might become just by happenstance so overwhelming in the lexicon that when you pull out the forms to compare it to, the current test form to, you never. Why don't you just happen to pull out all the things that behave uniformly and get a majority rules effect?
I think it's probably because the toy data I'm presenting it are so like 50%, like everything's 50% at the beginning. So probably if I gave it something that looked more like a real linguistic pattern, which usually are not at 50%, they're usually like closer to one end or the other, probably you'd see more of that emerging.
Okay, so then do you think that this might be able to model a variety of kinds of situations, one where you get stable variation, but then other things where you do get a categorical situation, and maybe the difference between them is you have different starting points?
Yeah, maybe that's definitely worth exploring. Yeah.
Okay, thank you.
And also like the complexity of like the grammar too, because I gave this an extremely simple grammar, it just has one Martinus constraint. But if it had more Martinus constraints, it would be sort of harder to learn each one, because there would be fewer lexical items that pertain to it. So if it looked more like the actual comparatives, for example, not that many adjectives actually end in liquids. So you can only learn the weight of that OCP constraint if you're looking at the liquids, right? So it just makes things a little more complicated. And I suspect in a situation like that, you'd be more likely to like sometimes accidentally just like only sample one kind of word or something like that.
Okay. All right, thank you.
Ed, hello.
Hi, this was great fun to listen to. And it reminds me a little bit of some of the discussions that Steve Pinker and others were bringing forth, and like Gary Marcus's work especially having to do with the U-shaped curve in kids. And I mean, I could only tell with the graphs moving towards 50 generations of iteration, but it seemed to be a fairly progressive trend towards the C-shaped distributions. But I wonder if it's possible, or what you think about a stage at a certain number of iterations of learning that might predict the U-shaped curve that they all talked about quite a bit during child language acquisition, where you might expect to see at some number of generations, I'll make up numbers, between the generation 150 and 300, you see a greater increase in categorical distributions at some set of frequencies, and then trending back towards the C-shaped curve that we see at the end of all the chart sequences that you showed us. I hope I'm making sense to you in this.
Yeah, I think so. Okay, so I think the way to understand this model that I presented today is that the U-shaped learning is like a property of like kids learning their native language, right? So where you would expect to see the U-shaped learning is actually within a single generation's learning rather than like across the generations. And in the simulations I'm trying to think of like a good example of this, but in the simulations I've run, you do sometimes get U-shaped learning, which is kind of interesting because at the beginning of learning, the model will always learn a phonological form constraint for every word. So it will get every word right for a while. And then once it hits the point where like those original phonological form constraints have decayed away, then it will start making errors. But that's also the same time where it really starts to learn the grammar. So you do kind of get this like U-shaped learning a little bit where it will like learn a bunch of words correctly, and then it will slowly forget them and learn the grammar. I don't know if that's like the same explanation that people typically give for children's U-shaped learning.
In those, I mean, that's a very interesting response, and I appreciate it because I think it does mark a connection between the two in the sense that early in the learning process, you might have what could be called a representation of simple higher level memorization, right? More reliance on the memory or the forms heard, they'll often say. And then the over-regularization that they always talked about during the U-shaped dip was as the rule system was kicking in. So it accords exactly with what you're saying there. Thank you.
If there are no more questions, then let's thank our speaker.